What if two objects, no matter how far apart, I mean, even billions of light years were fundamentally linked,
Uh-huh.
so deeply connected that, a change to one instantly affected the other, like right away?
Instantly, yeah.
Welcome, everyone, to the truly mind-bending universe of quantum entanglement. This is a cosmic long-distance relationship that genuinely baffled even Albert Einstein.
It really did. It's a phenomenon Einstein famously called spooky action at a distance.
Spooky action, right?
Yeah, because, well, on the surface, it just seemed to contradict his own really fundamental ideas about the speed limit of the universe.
The speed of light.
Exactly. It's one of those quantum concepts that just completely turns our everyday intuition about reality on its head.
It's pretty astonishing. And in this deep dive, our mission is really to unravel the core mysteries of quantum entanglement for you.
Yeah, we'll explore exactly how these particles manage to keep this bizarre connection across, vast distances.
And why it looks like it defies the speed of light. But maybe it doesn't.
Right, how it actually upholds it, and also how scientists finally, definitively proved this spooky action was real.
Get ready for some serious aha moments, folks.
Okay, so let's start right at the core. What is quantum entanglement?
The basics.
Basically, it's this phenomenon where two subatomic particles become linked up
Linked how?
in such a way that they essentially share the same quantum state. And the kicker is, what happens to one instantly influences the other.
Instantly, no matter how far apart.
Doesn't matter. Could be feet, could be light years. The distance is irrelevant to the connection itself.
That instantaneous part is what's so wild. It's almost like they're, two halves of a single thing.
That's a good way to think about it, even when they're far apart.
I remember reading about physicist John Bell back in, 1964?
Uh-huh. Bell's theorem.
Right. He really pushed this idea, didn't he? Saying these changes happen immediately, which I guess challenged the physics at the time.
Oh, absolutely, because decades before Bell, Einstein had already shown that nothing, absolutely nothing, can travel faster than the speed of light.
The universal speed limit.
Exactly. So this idea of an instantaneous connection across space, it just fundamentally clashed with everything he understood. That's where the spooky quote comes from.
He thought there must be something else going on, like hidden information.
Precisely. He suspected some kind of hidden variable, some underlying property of the particles that determine their states from the start. We just couldn't see it yet.
Okay, so to really get entanglement, you're saying we first have to tackle quantum superposition.
You really do. They're deeply related. For anyone diving into quantum mechanics, superposition is often like the first big hurdle for your brain.
Yeah, it's weird. I like Alan Migdal's analogy from the Joint Quantum Institute, the flipped coin one.
Oh, yeah. The coin analogy is great. Explain that one.
Well, the idea is it's not just that you don't know if the spinniest wing is heads or tails until it lands and you look.
Right.
It's that before you look, the coin genuinely exists as both heads and tails simultaneously. It's in a superposition.
And that distinction is crucial. It's not about our lack of knowledge. The state itself isn't definite until measured.
Yeah, that still kind of bothers me,
It bothers a lot of people. You're in good company. It's the whole point of Schrödinger's cat, right?
The cat in the box,
Hmm.
both alive and dead.
Until you open the box and observe it, particles really can exist in multiple states at the same time. That's superposition.
Okay, so how does that mind-bending idea connect to entanglement then?
Well, entanglement is basically a special kind of superposition. But here's the twist. It involves two separated locations in space.
Ah, okay, two locations.
Yeah. Think about a single photon hitting a beam splitter that has a 50-50 chance of letting it pass through or reflecting it.
Right, so it goes one way or the other.
That's our normal classical thinking. It went down path A or path B, and we just don't know which one yet.
But that's not the quantum reality.
Nope. The quantum reality is the photon is in a superposition of being in path A and path B at the same time until you measure it.
So it's literally in both places.
In a quantum sense, yes. This seeming absurdity, as you might call it, was exactly what Einstein, Podolsky, and Rosen pointed out in their famous 1935 paper, the EPR paradox.
They were saying this is just too weird to be true.
Essentially, yeah. From a classical view, it seemed impossible. They argued there had to be more to the story, those hidden variables again.
Okay, give me a particle example.
A really clear one is the decay of something called a Pime Mason. It's a subatomic particle. It doesn't live long.
Okay.
When it decays, it naturally creates two entangled partners, often an electron and a positron, and crucially, they have perfectly opposite spins.
Opposite spins, like one spinning clockwise, the other counterclockwise?
Sort of like that, yeah. We usually call it spin up and spin down, so if you
What?
measure the electron spin and find it's up,
Then the positron.
it's instantaneously down.
Yeah.
Guaranteed, even if they're now billions of miles apart.
Wow. Instantly. That immediate perfect correlation. That's entanglement.
That's the heart of it. A truly bizarre natural link.
Okay, so that's the theory. But how do scientists actually, see this?
Yeah.
Demonstrate it in a lab. You mentioned light earlier.
Right. Let's go back to Alan Migdal's examples. A common experiment uses photon polarization,
Polarization.
like sunglasses.
Exactly like that. It's the direction the light wave's electric field oscillates. Vertical, horizontal, or, somewhere in between.
Okay.
So imagine a special light source. It spits out 2 photons at a time, and they're entangled.
Entangled.
Their individual polarizations are totally random. Could be vertical, could be horizontal. But they always match each other.
Always match.
Always. So you measure photon A over here. Let's say randomly you find it's vertically polarized.
Okay. Random outcome. Vertical.
Then its twin photon, even if it's miles away, when you measure it, it will always be found to be vertical too.
So the first measurement somehow sets the state for both, even though the outcome was random. Precisely. It's like having a pair of magical dice.
Magical loaded dice.
Kind of. You roll one, get a random number, say a 6. But then you instantly know the other die, wherever it is, also landed on 6.
Even though the 6 itself was random.
Right. The result is random, but the twins' measurement will perfectly match that random result.
This should bother you, right? Our classical brains just don't work this way.
They absolutely don't. And it leads straight to the big, obvious question.
Faster than light. If measuring one photon instantly sets the state of the other one, way over there, did information just break the speed limit?
Exactly. Imagine that second photon is measured on, say, Pluto.
Okay, Pluto, that's what, 6 hours away at light speed?
Roughly, yeah. So you measure photon A here on Earth. How could the photon on Pluto instantly know what state it should be in? It seems like FTL communication.
It's not. This is where it gets clever.
This is where quantum mechanics pulls a fast one, you could say. It avoids that astronomical speeding ticket.
How? You couldn't, use this to send a message faster than light. Tell someone on Pluto the lottery numbers instantly.
No, unfortunately not. You couldn't send a stock order or the lottery numbers or any useful message faster than light.
Why not? What's the catch?
Here's the mind-bending part. While the particles are instantly correlated, the information that seems to travel faster than light, it isn't controllable information.
It's random.
It's pure, unpredictable randomness. When you measure photon A, you get a random result, vertical or horizontal. You can't choose that result.
Okay. I can't force it to be vertical to send a 1 bit.
Exactly. You just know that whatever random result you get, the photon on Pluto will instantly match it. It's a correlation of random events, not a communication channel.
So it's like we both have magic coins. We flip them. They land randomly, but they always land the same way. I can't use my coin flip to tell you anything specific.
That's a perfect analogy. The correlation is instant, non-local, but the information content of your measurement outcome is 0 because it's random.
So only randomness appears to travel faster than light. Clever. Special relativity is safe.
Special relativity remains intact. No FTL messages.
Okay, so if it's just random correlation, is it actually useful for anything besides being weird?
Oh, absolutely. That inherent randomness isn't just a quirk. It's actually a really valuable resource.
How so?
Well, it guarantees 2 things. Randomness, which is useful in itself, and fresh randomness.
Fresh randomness, what do you mean?
Think about generating random numbers for, say, cryptography or even a lottery.
Okay.
If those random numbers existed for a while before you used them, maybe someone could find a way to copy them or predict them.
Right, like a security risk.
But with entanglement, the random outcome doesn't exist until the moment you measure it. It guarantees the randomness was generated very recently.
So it minimizes the window for someone to hack or cheat the system.
Exactly. It's a fundamentally secure way to generate truly unpredictable random numbers on demand.
Interesting. So, okay, this all sounds incredibly strange. How did scientists actually go from Einstein's spooky skepticism to, proving this stuff?
Well, it took a long time. For decades, scientists were really grappling with it, even after Bell's theoretical work in the 60s.
People were still divided, still thinking maybe Einstein was right about hidden variables.
There was definitely still debate. because fully testing Bell's ideas experimentally was incredibly difficult. You had to rule out all sorts of loopholes. The technology just wasn't quite there for a long time.
So John Bell's work in the 60s,
Mhm.
that was the key theoretical step.
Absolutely. Bell didn't just say, this is weird. He devised a concrete mathematical way to test it, Bell's inequality.
An inequality, like a math equation.
Sort of. It basically set a mathematical limit. It said, if the world works classically with hidden variables determining things beforehand, then the correlations you measure between entangled particles can only be so strong. They can't exceed a certain value defined by his inequality.
Okay, a classical speed limit for correlation.
Exactly. But if quantum mechanics, with its spooky entanglement, was right.
Then the correlations would be stronger. They'd violate Bell's inequality.
Precisely. So the mission became build an experiment sensitive enough to actually measure these correlations and see if they broke Bell's limit.
And that finally happened.
The big breakthrough year was really 2015. 3 different independent research groups managed to perform experiments that were essentially loophole-free.
Closing the gaps in previous tests.
Right. And all 3 found results that violated Bell's inequality, supporting quantum mechanics.
Wow. Can you tell us about one of those experiments?
Sure. One key study was led by Christer Shalm over at NIST, the National Institute of Standards and Technology.
Okay, NIST. What do they do?
They use these incredibly sensitive detectors, superconducting nanowire single-photon detectors, SNSPDs for short.
That sounds complex.
It is. They have to be cooled way down to cryogenic temperatures, almost absolute zero,
Why so cold?
to make them sensitive enough to reliably detect a single photon. When a photon hits the supercooled nanowire, it creates a tiny hotspot, makes it momentarily conductive, and generates a detectable electrical blip.
Incredible precision.
Exactly. This precision allowed them to measure the entangled photons and their correlations with extremely high fidelity, really nailing down whether one measurement instantly affected the other, ruling out those loopholes.
And the result?
They published in Physical Review letters. The conclusion was pretty clear-cut. One of the co-authors, Francesco Marsili, basically summed it up. Bell was right.
So no hidden variables.
Any model of the world that tries to use local hidden variables simply can't explain the results. You have to allow for this non-local influence, this entanglement. The spooky action is real.
Which ties into the Nobel Prize recently, right?
Exactly. The 2022 Nobel Prize in Physics went to Elaine Aspect, John Clauser, and Anton Zeilinger. Their pioneering experiments, building over decades, were the ones that systematically closed loopholes and ultimately proved Bell right, ruling out local hidden variables.
So, case closed on hidden variables. But just to reiterate, this still doesn't mean faster than light communication.
Correct. It's crucial to remember that. Even though the measurements are correlated instantly over distance, no usable information is transmitted faster than light. Special relativity holds firm.
Okay. So, proving Bell's theorem was a huge win for fundamental physics. But does it have legs? Are there practical uses coming out of this beyond just proving a theory?
Oh, absolutely. This isn't just abstract physics anymore. The technology developed for these experiments has direct applications.
Like those SNSPD detectors.
Exactly like them. They're incredibly useful for quantum cryptography, building truly secure communication systems based on quantum principles.
Unhackable communication.
That's the goal. And also deep space communication.
Really? How does that work?
Well, remember NASA's Lady mission to the moon back in 2013, 2014?
Vaguely, yeah. Lunar Atmosphere Dust Explorer.
That's the one. It had a demonstration on board called the Lunar Laser Communication Demonstration. It used highly sensitive detectors, similar in principle to SNSPDs, to receive laser signals from Earth.
Ah, using lasers for high bandwidth communication.
Exactly. It showed the potential for these sensitive detectors in building arrays that could handle much higher data rates for communicating with faraway space probes, downloading huge amounts of science data.
So, better connections across the solar system, potentially enabled by tech from quantum experiments.
That's the connection, and of course the elephant in the room, quantum computing.
Right. Entanglement is key there, isn't it?
It's absolutely fundamental. Entanglement is one of the core resources, along with superposition, that gives quantum computers their potential power. Harnessing these entangled states allows them to perform calculations far beyond any classical computer.
For things like drug discovery, materials science.
And potentially, yes, even running complex simulations or optimizations for deep space missions someday. The technologies feed into each other.
So, wow. There we have it. We've taken quite the journey into quantum entanglement.
You really have.
We talked about this really surprising, totally counterintuitive link between particles.
Yeah, how they stay connected no matter what.
How it's been proven experimentally, defying classical intuition, but
But opening doors to some really amazing new technologies.
absolutely. What seems like really abstract fringe physics turns out to have very real relevance for all of us.
Definitely. It's impacting communication security, how we talk spacecraft, and the whole future of computing.
It's fascinating. But, even though quantum mechanics predicts probabilities with incredible accuracy, many scientists still wonder if it's the complete picture of reality. Is there more to it?
That's the lingering question, isn't it? Despite its successes, does it fully describe what's really going on underneath?
So as we wrap up this deep dive, maybe that's the thought to leave you with. What more remains to be discovered about this truly mysterious, deeply entangled world we live in?
Something to ponder, definitely.